My colleagues, and I want to pick up on chapter 6 here. And I left off here. I wanted to show you some more of these videos because they're actually very good. So let me show you this one.
Computing the yield to maturity of a coupon bond. In this example, we're returning to the cash flows of the bond that we looked at in example 6.3. Now we know the price, and we want to solve for the yield to maturity. It turns out that the only way to do that in a coupon bond is trial and error. And so we could do that by hand, but it would be pretty tedious and it would take quite a long time. Thankfully, Excel will do it for us. It'll just do trial and error really, really quick and find the solution quite quickly. It has a built-in function for doing this, the rate function. So I've redrawn the cash flows of the bond here on top of the Excel spreadsheet. They're $11 coupons paid every 6 months for 5 years, so that's a total of 10 6-month periods over 5 years, and a $1,000 par payment at the end. So we're going to use the rate function in Excel. So I'm just going to type equals to let it know we're computing something, rate, and as soon as I hit parentheses, it knows I'm using the rate function. It pops up its handy reminder of what it's looking for. So it wants n per, or number of periods, and so there's 10 6-month periods. Since the cash flows are paid every 6 months, we have to do everything in 6-month periods. The cash flows, the payment, are $11. Now, the PV is the price. The present value of the cash flows is the price. The way the formula in Excel works, the present value has to be the opposite sign of the cash flows. So we're going to put this as negative 963.11. And the future value is any final cash flow that's different from the regular cash flows. So here we have regular cash flows of $11 every 6 months, and we have a final cash flow of a $1,000 par payment. So I'll put in 1,000. Type is if I want to change the timing of the cash flows. We don't want to do that. And a guess is if I want to help Excel with an initial guess. It doesn't need my help. And so let's go. It turns out that the answer to the question, what yield to maturity will make the present value of these cash flows exactly equal 963.11, is 1.5%. Now it's very important to remember that since we did everything in 6-month intervals, what it's given us is a 6-month rate. And rates in the bond market are typically quoted as APRs. So we need to take this 6-month rate of 1.5% and double it to make it a 3% APR compounded semi-annually if we were to actually quote the yield to maturity of this bond.
Okay, so that was good. So here they show you how in this problem the 5-year $1,000 bond. Okay, that's the term, right? The maturity is 5 years. This is the par value, and here's the coupon rate. So you'll either get $50. Okay, so it's semi-annual. So you will get $25 every 6 months. And the question is, what price is the bond trading for now? And you could either use this equation or plug in here 10 periods, 3.5, and here's the price, right? 3.15%, right? So remember that's 6 months, so this is 6.3%. So you take half of that. Here's the payment. Here's the future value. It's 6-month periods, right? So there's the price. That's what the current bond is trading for. All right, let's go through this one now. We've got all these nice examples here.
Computing a bond price from its yield to maturity. By now we're getting pretty familiar with this bond. It's the bond we've used in example 6.3 and 6.4. It's a $1,000 par bond. It's got 5 years to maturity and a 2.2% coupon, meaning it pays 2.2% of the $1,000, or $22, every year. But those coupons are paid semi-annually, once every 6 months, at $11 every 6 months. So you get a total of $22 every year. Now, in this example, interest rates have changed, and so the bond's yield to maturity has decreased to 2%, and we want to know what's happened to the price of the bond. Okay, so if you recall, we're going to do everything in 6-month intervals because that's how often the actual cash flows are paid. So we've got 10 periods, 10 6-month intervals in 5 years. It pays $11 every 6-month interval. You get $1,000 par at the end. That's the future value. The yield to maturity is now 2%, but that's 2% APR semi-annually compounded, and we have everything expressed in 6-month periods. So 2% per year with semi-annual compounding is actually 1% every 6 months. So we're going to enter 1 as our interest rate here. And the calculator says interest rate per year, but it really means interest rate per period. If we do everything in terms of 6-month periods and we do the interest rate per 6-month period, everything is still consistent. So we have all the information, and now we just need to solve for the present value. Remember, the price of a bond is the present value of its cash flows. So let's compute present value, and we get $1,009.47. Remember, the way the financial calculator works is the present value is always the opposite sign of the cash flows. So it's representing this as a negative, but we know prices can't be negative, so you just think of it as $1,009.47. So the bond's price has gone up from $963.11 to $1,009.47 because interest rates have dropped, and so you now are expecting a lower return. So in order to get a lower return for the same cash flows, you have to pay more for those cash flows. So you pay more, and the return on your investment of more than $1,000 comes down to 2%.
All right. So and then there's another one here.
Computing a bond price from its yield to maturity. In this example, we're still using the same bond from examples 6.3 and 6.4. It's a 5-year Treasury note with $11 coupon payments every 6 months and a $1,000 par payment at the end in May 2018. And what's happening in this example is we're considering, what if interest rates drop and the bond's yield to maturity decreases to 2% APR compounded semi-annually? So it was 2.2%, economic news come out, and interest rates have dropped, and now its yield to maturity is 2%. And what's happened to the price of the bond as a consequence? So we can very quickly compute the price of the bond using the built-in Excel functions. So remember, the price of a bond is just the present value of the cash flows represented by the bond. So we're going to use Excel's built-in present value function. And again, as soon as I hit parentheses here, it knows I'm using the present value function, and it tells me exactly what it's looking for. So the yield to maturity is 2%, but that's a APR compounded semi-annually. And all of our cash flows here are paid in 6-month intervals. So everything has to be in terms of 6 months. So it's actually 1% every 6 months is the same as 2% APR compounded semi-annually. The number of periods is the number of 6-month periods left in the life of the bond. That's 10 6-month periods in the next 5 years. What's the payment? That's the coupon payment of $11 every 6 months. And what's the future value? That's the $1,000 future value paid at the end of the bond. It's par value. So that's 1,000. Type is an optional one if I want to change the timing of the payments. We don't want to do that. So we're done, and we ask it for the answer. And the answer comes out to be $1,009.47. It's expressed as a negative because the way the Excel function works is that the present value has to be the opposite sign of the cash flows. So in the new interest rate environment, with a lower yield to maturity, the bond's price is $1,009.47. Note that the bond's price has actually increased from before when it was $963.11 because interest rates have gone down. the bond's price has to go up so that if you buy the bond at the higher price, you're still getting exactly the same cash flows, but since you bought it at a higher price, those cash flows represent a lower return on your investment, and it lowers the return to just enough to make the yield to maturity be 2%. Stop.
Okay, so those were interesting examples, and I hope you understood them. So I want to make one point that's really important right here. When they price a bond, when it's quoted, and let me highlight this because this is important. It would be quoted. It's not quoted. It's quoted as a percentage. So it's quoted as having. You notice how they quote it here. It's a percentage of 94.498, which implies an actual price of 944.98, given a par value of 1,000. And you can see what it says here. They are conventionally quoted as a percentage of their face value. So I just want to make sure you understand that. So when you see it as this, it's really $1,000 face value, and they're just giving it to you as a percentage. Okay, I hope everyone was clear about that. All right, so bonds have a dynamic behavior. So zero coupon bonds trade at a deep discount, right? And that's that prior to maturity, their price is less than their face value. Coupon bonds may trade at a discount or a premium. Depends on what the price of the bond is, or they could be even at par, right? There could have been a new issue at par. So we're going to look at when a bond will trade at a discount or premium, as well as how the bonds prices will change. So we're going to look at the dynamic behavior of bonds now. And as I said, as interest rates change, so do the prices of bonds, okay? So bond prices are a function of the changing landscape of yield to maturity for new issues. All right. So I'm going to pick up on the next part right here because I'm 13 minutes in. I don't want to lose any material.